just did Lenz's law. So what Faraday did, he took Lenz's law, which is nice and explains it, but there's no math. We love math, right, Thornburg? That's right, buddy. It says we love math so much, we're going to try to put some mathematics behind it. And that's what Faraday tried to do. He did a pretty good job. It's not that hard at math. So we're going to look at Faraday's law and a little bit of the applications from it and kind of go from there. And this is one of the big accomplishments in magnetic field theory, understanding why and how induced currents occur. Okay. All right. So let's look at Faraday's law. Well, Faraday basically said, all right, there's an induced, there's a magnetic field that's created that causes an induced current. But what causes currents? Well, an induced current is caused by a changing induced magnetic field, which results in an EMF, electromotive force. In other words, something's got to there to push it. So what's the electromotive force? That's like a potential difference, some delta V between two ends of a wire. Okay, between two ends of a wire. Now, remember we talked about electromotive force the other day? It's going to be like this. It's really, you think of it as a change in voltage. Now, Lenz's law said you got to have a change in the B field. The changing B field is going to create an induced B field. Well, let's look at some mathematics. What is that rate of change? And a rate of change, what's that fancy word we use in mathematics nowadays? Mathematics has only been around 300 some years. It's called calculus. And so what is a rate of change? Rate of change. Nick, that is correct. Derivatives. Or as I like to say to upset my calculus teacher at the time, derivatize. I said, we're going to derivatize this function. And he'd look at me and go, gosh, stop it, honey, just stop it. And so what I do, I said, yes, sir, I will not derivatize any more functions anymore. I will quit derivatizing. And I will keep talking about quitting derivatizing. That's another story. Now, so what we're going to say is this induced EMF here. This induced EMF is basically just the magnitude of the rate of change of the flux. It's the change of the flux is what causes an induced B field over time, as a function of time. It's the magnitude of that rate of change of flux over time. Now, this is for one coil wire. Of course, if you have many coils of wire, it would equal N, I'll use capital N, that's a number, N d flux dt for N coils of wire. Let me make that F a little bit nicer, make Kelsey happy. Alright, so that is the induced EMF across that. That's your measurement of voltmeter. That's Lenz's law. And we're going to do an example here, like an MRI example, because MRIs can have changing magnetic fields. But let's think about this. It says, what is this telling us? So I'll say, but the flux we said earlier is B dot A. The flux is the B field dot product, doing a dot product with the area unit normal vector of that loop of wire. So let's put that in here. And I'm going to just use this one for one coil. We'll just multiply times N for multiple coils. We're going to say that Faraday's law is N equal to D, B dot A dt, the magnitude of it. Now, if that's the magnitude of it, how do we deal with taking a derivative inside here and two things multiplied together? Cameron, you're exactly right. You're awesome, Cameron, sometimes. It's the product rule. So let's look at the product rule. And that will basically say then that we will get, I'll write it like this, B dAdt plus A dBdt. It's the magnitude, whoops, of each. Well, no, that was wrong. I didn't write that exactly right. So it's B dot, this one, plus A dot that one. I get my vector stuff right. And I can put it over the whole thing, but that works for what we need to do. Now, so what is this really telling us here, this equation? So basically, the induced voltage is a product, it's a sum of the two different effects. This, let me get red here, this is how much, it's how much the area vector changes over time. Whether the area gets bigger or smaller, whether it, starts moving around, boogieing around and stuff like that. All right? So that could be part of what's causing the induced current. It can also be here. Do this way. This part is how much the magnetic field changes over time. And that, since it's a vector, that could be the strength of that field or the direction of the field. So it's taken into account this one equation right here, actually right here, takes into account both of those because flux deals with the magnetic field and its strength and direction, dotted with the area unit normal vector, how big that area is and its direction. And those two things, those two effects added together give the EMF, or the induced voltage, between 2 points on the wire. Okay? That's what's going to give it. Right, now that's theory. That's cool theory. I like it. Let's get something, do an example. And I actually like the current induced by the MRI machine, because MRIs, some of you may have had an MRI. Look at the current induced. Now this is example 30.9 in your book. So let's look at the 30.9 in your book. We're going to work that problem real quick. Irving, you can't help me erase the board to make this go quicker. I'm sorry, just take notes. Keep working hard on the board. Okay? All right, 30.9. Current induced by an MRI machine. Should be A, I think. Yep. And it sounds like it should be N, but A. All right. Who wants to read the problem for me? No volunteers. Oh, that's not good. Y'all a little shy today. I'll read the problem. Alright? The body in a conductor. The body, excuse me, is a conductor. Help if I had reading skills. The body is a conductor. Not musical conductor. So rapid magnetic field changes in an MRI machine can induce currents in the body. To estimate the size of these currents and any biological hazard they might impose, because Consider the loop of muscle tissue shown below in figure 30.29. This would be a muscle circling the bone of your arm or thigh. Although muscle is not a great conductor, its resistivity is 15 ohm meters. 1.5 ohm meters, I'm sorry. I hope I knew what the decimal was. We can consider it to be a conducting loop with a rather high resistance. Okay. Suppose the magnetic field along the axis of the loop drops from 1.6 teslas, that's a lot, to 0 teslas in about 0.3 seconds, which is the largest possible rate of change for an MRI machine when this book was written, when this problem was written. So what current will be induced? So we're going to have to figure out, looks like we're going to have to figure out the rate of change of the flux. From that, get us a voltage, and from that voltage, that induced voltage, from that, get us a current. And see if that's enough current to start you twitching. And stuff like that. My medicine helps me so I don't twitch. Now, so let's just kind of go through the problem. Okay? Alright, so let's draw our picture. And we got our, here's our kind of muscle. It's in a loop. So you can think of it as basically a loop here. Alright. Now we got the B field, according to the book. B field is going to be doing like this. So you got a B field going through this loop. Now, they draw this so that it is like this. Now, what they're basically assuming is, it looks like here, that this rate of change, this flux is, they already tell you the B field. So we're going to find, and they're going to basically say this is circular here. This is circular. Since the B field is parallel to the axis of the loop, so what we're going to say is that the electromotive force, d phi dt, the magnitude of it, we're going to say this is equal to pi times radius squared dB dt. How can we say that? Well, what is flux? Magnitude times area. If they're perpendicular, we're going to say that in this case B is parallel to A. So B dot A is just going to be equal to B times A, or the magnitude of the two vectors, right? And what's the magnitude of the circle? Over here, some circle R is just pi R squared times B. And that's the flux. And that's how they got that. Alright? So, how fast does this flux change? Pi R squared? Well, we say the B max, it said, was 1.6 Tesla, and B min is 0, and the delta T to do that is 0.30 seconds. So that's going to be here. The change in this, that's 1.6 minus 6 Tesla minus 0 Tesla over 0.30 seconds. Remember, a derivative is just how much it changes, point to point. So it's like a slope, remember. This is all we did here. So if you do that, what will you get? Well, according to the book, you get 5.3 Teslas per second. Now the book has a negative here. You know why it has a negative? Because I made a mistake. When you do a derivative, you do final minus initial. And I did initial minus final. Bad duck. Okay, I should have done that. So, final minus initial is 0 Tesla minus 1.6 Tesla. So that was my bad. Alright. And when we get our sig figs right, I'd make this, of course, 0.0. Kelsey's on to me about those sig figs. All right? So you get 5.3 Teslas. Now, we're making the assumption, and they throw this in at the last minute, that this R here, that R is 0.04, make sure I got that right, 0.040 meters. 0.040 meters. So I think that, if that's R, and what is this R of? That's of the muscle. And so how big is this? Well, that's 4 centimeters. 4 centimeters, about 1.5 inches. No, 1.5 inches is like that. So that would be kind of a small, it's not like a thigh, but it's just a loop of it. We're going to assume a loop that big. I don't know why they did it, but that's what he assumed. All right, so if we do that, and of course that's times pi squared. To get the flux, we need to take pi times 0.040 meters times negative 5.3 Teslas per second. And in that case, the flux then is equal to the change in. My apologies. I wrote flux, and I am not good today. This is a bad day for me. The induced EMF. Too many of these dang videos I'm making, I guess, right? So this induced EMF, or the voltage on there that we get, according to the book, is 0.027 volts. And 5 times 0.04 is about 0.2. Oh, I didn't square it. I think that's squared. Yes, that becomes, yeah, that's about right then. 0.04 squared is 0.0016. So that moves that over to that's about right. 0.005. Alright, yep, that works. Okay, so if that's the voltage in it, how are we going to find the current? Well, we're assuming a current loop. So we're assuming this is like a resistor, right? So we know V, delta V equals I times R. And the resistance of that, now they did say that the resistivity rho of this is equal to 1.5 ohm meters. And if you assume that area and you do a little conversion, and they kind of gloss over that, they say with these values we can compute. So if you go back and compute resistivity to resistance, it's resistance equals rho L over A, if I'm not mistaken. The length of it divided by the size of the cross-sectional area of that wire, or whatever. But basically they say that this gives, you can calculate it, which was a little, the book showed it more than this, but they get 4,700 ohms. And since it's a muscle, it's fairly high resistivity. High resistivity, that's about right for a resistor, for the resistor value of, with a circle of that radius. That sounds about right. So if we know that then, find the current, that's just delta V over R. And the induced EMF, 0.027 volts over 4,700 ohms. And if you do that, let's everybody pull out their calculators and do this. Pull out your calculators. Includes you, Ronnie. Pull your calculator out as well. Okay. All right. Frito, what you get for an answer? Of course, Frito, you were right. We get about 5.7 microamps. Now, yes, you could have wrote it with, said it with all the decimals like you did, but let's just write it as microamps. Since it's a microamps, you know that's 5.7 times 10 to the what, Frida? Right. -6 amps. Now, is that enough to make a darn bit of difference in your muscle? You start twitching over that? Nah. You'll be fine. That's going to be safe. All right. So yeah, I think you're good with the MRI like this. Okay. That's Faraday's law. Rate of change of the flux, the time rate of change of the flux, I should say, is equal to the induced EMF.